In this video, we will look at collections in Mobius. In the Mobius Spatial Information Model, geometric entities are organized into a hierarchical data structure. There are three main layers. At the top are collections of objects. In the middle are objects. And at the bottom are positions. A collection is an aggregation of points, polylines, and polygons. In the example, a collection has been created that contains a set of polygons. In the viewer, collections can be selected as single entities. In the attribute table, under the Collections tab, we can see a list of collections. In this example, we can see that there is a collection called block. To create collections, the collection.create function can be used. The parameters for the function are a list of entities and a name. Both parameters can be null. If the entities is null or an empty list, then no entities will be added to the collection. If the name is null, then the collection will not have a name. In this case, we first create an empty collection called block. Once a collection has been created, you can add and remove entities. In the example, the collection.add function is used. We add the base polygon and the list of block polygons to the block collection. A collection can be heterogeneous. So YU can add any type of object. In the example, we create some polylines representing handrails. The polylines can be added to the same collection. The collection now contains both polygons and polylines. Note that positions and topological entities cannot be added to collections. They are not objects. Objects can also be added to more than one collection. In the example, we have three collections. One for each block. And one for all walls. The wall polygons are all in two collection. In their block collection. And in the walls collection. Next, we will look at various aspects related to collections in more detail. The util.entityInfo function can be used to understand what is inside your collection. In the example, we can see that the function has been called 2 times. Once for the walls collection and once for the block collection. The walls collection contains 40 polygons. The blocks collection contains 22 polygons and 5 polylines. The same function can also be used to print information about objects. This will allow you to see which collection an object belongs to. In the example, we are printing the information on one of the walls. We can see that the wall belongs to 2 collections, block and walls. Collections can also be used with many of the modeling operations. For example, you can copy, move, rotate, mirror, scale and transform collections. Collections can also be deleted. Doing so will delete everything in the collection. Many other operations will also work with collections. For example, color can be applied to a collection. This will create an RGB attribute for all the vertices in the collection. Next, let's consider attributes on collections. Collections can also have their own attributes, just like any other entities. The ability to create semantic attributes that relate to the whole collection can be very useful. In the example, we add 2 attributes to the block. The first attribute specifies the number of floors in the block. The second attribute specified the gross floor area of the block. Semantically, these attributes make more sense when they are attached to the whole block rather than to individual polygons. The same shorthand expressions for getting and filtering also work with collections. 2 examples are shown here. The first gets all the collections in the model. The second gets all the collections with the name block. Note that in the second case, The collection.get function can also be used. Collections can also contain other collections. This creates a hierarchy of collections. For each collection, we can refer to the parent collection and the children collections. A collection can only have one parent, but it can have multiple children. In the attribute table for collections, there is a column that identifies the parent of each collection. If a collection has no value for the parent, then it means that the collection is at the top of the hierarchy. In the example, we can see that collection 0 has no parent. Collections 1, 2, 3 and 4 have collection 0 as the parent. The util.entityInfo function can be used to reveal the collection hierarchy. In the example, we can see that all blocks collection contains 4 child collections. Each child collection contains a set of polygons. Attributes can also be pushed to from collections. We will look at 2 examples. In the first example, an attribute is pushed from the polygon level to the collection level. For each wall, a glazing area has been calculated. This area is then pushed up to the collection, using the sum method. In the collections attribute table, the new column can be seen for glazing area. The value will be the sum of all the glazing areas in that block. The second example looks at pushing attributes from child collections up the parent collection. When selecting the push method, the drop-down menu lists 2 additional targets. Co-P stands for collection parent. Co-C stands for collection children. In the example, we push from children to parents. We push the glazing area from the block collections up to the all blocks collection. Next, we will look at how collections can be used for passing data between nodes. Previously, we have advocated using attributes as a way of communicating between nodes. An upstream node may generate some polygons that a downstream node needs to use. In that case, the upstream node can add attributes to the polygons. The downstream node can then query the model and retrieve the polygons it needs. This approach works well. However, it can result in a lot of attributes. Collections offer another way of passing data between nodes. One advantage of using collections is that it results in fewer attributes. In addition, collections also tend to make the semantics clearer and easier to understand. Let's focus on the data being passed from the skeleton node down to the other downstream nodes. The skeleton creates 16 polygons, grouped into 4 collections. The A, B, C and nodes each need to retrieve one of these collections. The colors nodes need to retrieve all 4 collections. We need to define our attributes to ensure that we can either get a specific collection, or get all collections of some type. There are many different ways this could be done. One approach is to define 2 attributes on the collections, name and type. The name attribute can be used to give a specific name to each collection. The type attribute can be used to assign a generic type to each collection. If a specific collection needs to be retrieved, then the name attribute can be used. This can be done in 2 ways. Either a query expression can be used, or the collection.get function can be used. The example uses the latter. If multiple collections of the same type need to be retrieved, then the type attribute can be used. In this case, the collection.get function cannot be used since that only works with name. So a query expression can be used. The final model contains a hierarchy of collections. If you change the selection setting to collections, you can select each collection in the viewer. If you switch on the eye for the floor area attribute, you will see the total floor area displayed for each collection. You can now play a density game. Look at the blocks and try and guess which has the highest floor area. Then click on each block to see if you got it right. That brings us to the end of this video.